Hello, friends of linguistics. I'm Dirk Gerards. I'm Professor Emeritus of Linguistics at the University of Leuven in Belgium. And it is my pleasure of hosting today's talk by Dagmar Divjak. It's a talk in the Abralin au Vivo series, a series that has become a treasure trove of up-to-date talks on all matters linguistic. To briefly introduce the speaker, Dagmar Divjak studied Slavonic philology at the University of Leuven, where she obtained her PhD in 2004. In 2006, she joined the University of Sheffield, where she left in 2019, moving to the University of Birmingham as professorial research fellow, and it is in that capacity that she is currently leading the Out of Our Minds project that she will talk about in a few moments. Among her many publications, let me just mention two monographs, Structuring the Lexicon of 2010 and Frequency in Language of 2019. In addition, she edited the Handbook of Cognitive Linguistics, published by De Gruyter in 2015. And she is also, importantly, editor-in-chief of the journal Cognitive Linguistics. So all of this should be sufficient evidence that she is one of the leading voices in current usage-based linguistics. And that is why we are extremely thankful that she has accepted to present a talk in the Abralin series. I'd like to remind the audience that questions and comments can be formulated in the YouTube chat, and there will be time for discussing them after the talk. So without further ado, let's turn to the computational turn in usage-based linguistics. Professor Divjak, the screen is yours.
Thank you, Dirk. I hope this is all right, and you can see my slides. So thank you so much for inviting me to talk in this series. And today I'll be presenting a few studies that I hope, or we hope, my group hopes, will be the beginning of a computational turn in cognitive linguistics. And I will start by outlining what we are trying to achieve in the Out of Our Minds research team, and then dive into some case studies. So as you all know, usage-based linguistics is built on a number of assumptions. One of the key assumptions is that languages are dynamic systems that emerge from and are shaped by usage in a process that's mediated by general cognitive abilities and functional considerations. And the general cognitive abilities that have received most attention to date are things like classification, generalization and abstraction, but also imagination. And at the same time, there are some cognitive constructs that appear very important, but that have received less attention. And examples here are memory and attention. Memory, for example, should be something that's widely discussed because frequency plays such a crucial role in usage-based approaches, and frequency effects are in essence memory effects. So despite our interest in the emergence of structures from use, processes or functions that would enable growing such a system from use have been absent from usage-based considerations. And in fact, learning constitutes what I like to call our very own elephant in the room. Learning was exiled vigorously from the linguistics landscape by Chomsky's criticism of Skinner. So Chomsky in 1959 published a very influential and very negative review of Skinner's verbal behavior. And although since then many years have passed and recent years have really seen a resurgence in the interest in learning, learning is still to make a full comeback onto the linguistic scene. And I got interested in learning because I was looking for a way to ensure the cognitive reality of the categories and the labels that I was working with in my practice as a linguist. As a cognitive linguist, a cognitive corpus linguist, the real conundrum for me was and still is knowing whether the patterns that I find in the data are real. And with real, I don't mean do these patterns exist in the data, because sure, they do, we found them. With real, I mean, are they real for naive native speakers who aren't trained linguists? And I'm particularly interested in the question, or the questions of which regularities are discovered and exploited by language users who aren't trained linguists. What do these patterns look like? Is it really necessary for us to make sense of these patterns, to attribute meaning to them? And once we know what these patterns look like, we can also start thinking about what the corresponding abstractions could contain. So these are some of the questions that really bug me. And one way for me to get a handle on this is via the concept of learning. And when we talk about learning in our team, which consists of linguists and psychologists, we came to a few interesting conclusions. So when we asked the psychologists what they think of linguistics, they said, well, linguists are basically interested in the end result of learning. So we like our knowledge neatly organized, as in this tool cabinet here on the slide, which has a space for phonemes and morphemes and lexemes and constructions, you name it, we have it. And of course, when you ask a linguist what they think of psychology, we will say that, you know, psychologists are interested in the process of learning. This is how the rat learns to navigate the maze, and they also like to know everything there is to know about their little individual rat. And in the Out of Our Minds team, what we're trying to do is we're trying to combine these partial interests, if we can call them that, of psychology and linguistics, because we think that the process can help us understand the end result. So what we want to do is let learning constrain the linguistic units and the generalizations that our linguistic theory would allow. For us, that's a way of honoring the cognitive commitment. And the end result can also help reverse engineer the process. The language system is one of the most complex systems that any human needs to learn, and it would be good for any theory of learning to be able to deal with that level of complexity. So we think that linguistic data really presents learning theorists with a nice challenge. So what you will hear throughout this talk is that when you merge these two insights, that of psychology and of linguistics, or these partial interests of psychology and linguistics, that maybe the neat tool cabinet that linguists used to work with actually looks a bit more like a messy drawer. And I'm saying that because grammar or the mental representations, representation is of course a very dangerous word, but I hope linguists know what I mean. What we think language users know about language may be a lot more concrete than we linguists assume. They may be much more concrete and much more faithful to the experience than the categories linguists typically operate with. And throughout our studies, it strikes us time and again that the abstractions that we find may not look the way we as linguists would expect them to look, and that the dividing lines, or the most important things that govern a phenomenon, may not be what we expect it to be. So in today's talk, I will present some of the work that we are doing currently on understanding the verbal system. And we factor learning in by using computational techniques that implement principles of learning. And I will talk to you more about that in a second. But first, I'd like to put in a few disclaimers. So you will see once we start talking about the computational model that this is not the most advanced computational model that's currently available. We are not aiming to do things as well as is computationally possible. Our interests, we're all cognitive psychologists or cognitive linguists, and our interests are in doing things as cognitively plausible as possible. And another thing I'm not trying to do is say or that learning is the ultimate answer. I'm not trying to convert the world to learning, let alone try to convince anyone that learning will solve all the problems of linguistics. It won't. But I do feel that learning has something very valuable to offer to the usage-based community, partly because it gives us a way to show or to study how abstractions might emerge from exposure to usage, and what the abstractions could be made of and would look like. Now, one of the things that to me is very attractive about a computational modeling approach is that you get a grip on the pipeline. So you have control over what goes in, you have control over what is processed, and then you see what comes out. And you can fiddle with the input, or you can fiddle with the algorithm to make the output resemble more closely what you see in real language. Of course, computers aren't humans, and although some algorithms currently are superhuman, typically when it comes to computational modeling, there is a significant degree of simplification involved, and this is often a stumbling block for linguists. I think there are other stumbling blocks too. In a chapter that Peter and I wrote for a forthcoming handbook of usage-based linguistics, we had a chapter, or we have a chapter about the computational turn in cognitive linguistics. And we very hopefully wrote that maybe the 2020s might be witnessing the very start of a computational turn that would see cognitive linguists engage with computational models to put the theories, their theories to the test. But of course, we also outlined some stumbling blocks. There are a number of things that sits, not so well with cognitive linguists. As you may remember from the quantitative turn on which Dirk Gerards led, one of the difficult things about computational turn is going to be the skills. There is a huge upfront investment in skills that is possibly even larger than it was or is with quantitative approaches. And we think that one of the solutions, if not the only solution to this problem, would be to start collaborating in interdisciplinary teams, which is maybe not something that comes very naturally to linguists. And then there's a second difficult thing about computational models, and that is that very often computational approaches rely on data sets that are so large that expecting any human intervention or oversight is unrealistic. And again, this is something that doesn't sit very well with linguists. We really like to get our hands dirty in the data. And thirdly, and this is a blessing as well as a curse, and that is that computational approaches require precision at an unprecedented level. So computers execute, but they do not interpret, and they need exact instructions. And typically these instructions are wrapped up in algorithms that, at least for now, address only a limited number of dimensions of a problem, and they tend to focus on those that are straightforwardly measurable. And I think this restriction in particular comes as a blow to cognitive linguists, because our work centers on meaning, and in particular on complex cases where the whole is more than the sum of the parts. And meaning is really core to the cognitive linguistic enterprise. And some would go as far as to argue that meaning is inherently subjective and cannot be approached with purely objective methods. But hopefully after this talk, you will find that the gains of computational approaches outweigh the costs and the disadvantages. So the case study that I will be presenting here, or both case studies, have to do with aspect. And aspect is a category, a verbal category that has attracted the attention of linguists for decades. It's also a linguistic category that has often been described by relying on semantic differences and semantic distinctions. So we found that it would be a very nice test case for our computational learning algorithm that in the end doesn't understand anything at all. So first I'll give you a very brief, very brief intro to aspect, more in particular to Slavic aspect, because the case studies we'll be looking at relates to Polish, which is a Slavic language. So in Polish, you have the verbal category aspect, and that category has two values, so to speak. It's imperfective and perfective. And as you can see in the example, the imperfective form and the perfective form are closely related to each other. In this case, the imperfective has an infix, whereas the perfective has not. And if you have a past imperfective verb, it would in this case translate something like they were winning the match, whereas the corresponding perfective past would translate something like they won the match. So this idea of aspectual pairs is really important in Slavic languages, because in Slavic languages, aspect has grammaticalized to the extent that there is no single verbal form without aspect. Even infinitives are marked for aspect. It's not like English, where you have the verb talk, and then you can go and create a present perfect or a present continuous. Even the infinitive talk, the corresponding form in Polish would be either imperfective or perfective. And as you can see, both aspectual forms differ slightly from each other. In the example on the previous slide, there was an infix, but most often there is a prefix added to the perfective form. As I said, all verbal forms in Slavic are marked for aspect, so there's no escaping aspect. You always have to make a choice. But you can't always choose. So inflectionally, there are notable gaps that apply without exception, such as here on the slide. You can see, for example, that the present tense cannot be formed using a perfective verb. There are other differences between the two aspects. For example, how the future tense is formed. Also in the voice for the participles and the gerunds that are available for imperfective and perfective, but this is not so crucial here. What is going to be important for this talk is that when you map aspect onto tense, there is one tense, the present tense, that only exists for the imperfective, but for all of the other cells, you have to choose between an imperfective or a perfective form. Now, to deal with the system, linguists offer the following. They present verbs in pairs. All dictionaries list for one English verb talk, there would be two Polish verbs, an imperfective and a perfective. These forms are slightly different from each other, but very often clearly related. Linguists also offer semantic rules that guide the choice of when to use the imperfective versus the perfective, and we'll see a few of those on the next slide. And sometimes also there are contextual elements that can help you choose if the semantic rules aren't sufficient. So, for example, this is taken from a textbook. If you are using an imperfective form, you are focusing the attention on the duration of an action or on the fact that the action was, is, or will be repeated. Whether the action was finished or will be finished is not important. And that's exactly the opposite of the perfective, where it's generally suggested that attention is focused on the result or the completion of an action, or on the fact that the action was or will be performed only once. So if you contrast two sentences, again, from a textbook, one is, she always bought food in the store. That would be the imperfective one. Sorry. And it says, as by way of explanation, this sentence uses an imperfective verb because it implies that she bought food in the store multiple times, not just once. If you use the perfective, for example, she bought food in the store yesterday, then the explanation would be that this sentence uses a perfective verb because it is implied that she bought food in the store only once, and this action was not repeated. Of course, this is a terrible oversimplification of the situation, but it is the way in which aspect is typically explained to foreign learners of Slavonic languages. Now, as I said, our team consists of linguists and psychologists, and when we started working on aspect and wanted to design our studies on aspect, and the linguists on the team were explaining the system to the psychologists, we had this really interesting situation because the psychologists were incidentally also native speakers of a Slavonic language, in this case, Serbian, which is a language that has an aspectual system that's pretty much like Polish, and they both objected, especially to the pairing of imperfective and perfective, and they said they strongly felt that all these verbs were different words, which struck us linguists as really funny. But actually, there is some psycholinguistic work on Serbian verbs that backs up their gut feeling. So Feldman and collaborators showed that there are differences in processing times for target verbs depending on whether they are primed by the same aspectual form or whether they are primed by a form that belongs to the other aspect. So the facilitation effect was stronger when both forms belong to the same aspect than it was when the forms belong to a different aspect. So maybe these forms really are different words. We'll see. And the interesting thing is also that whether aspect is a grammatical phenomenon or a lexical phenomenon, that's the essence of decades of discussions that linguists have been having. And in the literature, there are several ways to think about aspect, but the two prominent ones are quite literally the grammatical and the lexical approaches. So on a grammatical approach to aspect, the aspectual opposition is considered primary. That means it determines how verbs are used and what they mean. And the aspectual opposition is thought to apply to all verbs and have the same effect on all lexical items. You can clearly see the traces of structuralism here with the search for an invariant meaning. And this approach has been very influential in Slavic linguistics. Now, the lexical approach says more or less the opposite. It says that it's the meaning of the verb that determines which aspect can be used. And although this idea was first elaborated by a Russian linguist for Russian, it's the independent proposal by the philosopher Wendler that has made this approach the dominant one in Western linguistics. You will remember his 4 Aktionsarten. So this is in essence a search for semantic classes. And the 2 case studies that I will be talking about will hopefully shed some more light on the question of whether aspect is grammatical or lexical or something completely different altogether. So the first case study that I will be presenting is a computational learning study that was carried out in collaboration with Irene Testini and Petar Milin. They're both in the audience and they will join us for the discussion. As you can see, as you can tell from this slide, the study is still very fresh. We are wrapping up the manuscript. It's not been submitted yet for publication, so your thoughts and comments will be very welcome. Now, in a nutshell, in this case study, I want to ask 2 questions. The first question is, can aspect be learned from exposure to raw input or meaningless input, basically without understanding what aspect is thought to convey? And the second question is, what types of cues would be informative for the choice of imperfective versus perfective? And to what extent do they help us decide which form would be appropriate? Now, as I said, in computational modeling studies, you often use data sets that are far too large for any human analyst to handle. And we worked in this case with a data set that contained 10 million sentences, so not 10 million words, 10 million sentences from the Araneum Polonicum. That's a corpus that basically contains data crawled from the internet, and it has been annotated using the standard Polish part of speech tag set, but nothing more. So based on the tags that were available, we had to construct aspectual annotation. And we also had to link verbs together in terms of the aspectual pairs as they are usually used. So for that, we got a little help from our colleagues in Germany and Poland, who had very usefully constructed a list of 1,765 aspectual pairs. So there was a lot of work for Irene involved to get this really raw corpus set up in a way that we could at least recognize which aspect was being used, whether there were any aspectual pairs in the corpus, and also to annotate, to provide the basic annotation that we would need to run the study, to pick out the verbs to begin with. So although we did a lot of work in preparing the corpus for analysis, I will stress here that we excluded a number of situations. So we're mainly focusing on indicatives and conditionals, leaving out imperatives and infinitives and participles and gerunds and other exotic things, because there are additional difficulties with those in Polish. So first, as any good statistician would recommend you do, first we plotted our data. So on this slide, you see a plot of verb types. and the extent to which they occur in the imperfective, the perfective, or both. So as you can see, we had, recall we had 1,765 verbs. On this plot on the left-hand side, you see the first bar contains 600 different verb types, and all of those verbs occur more than 90% of the time in the imperfective. On the other side of the plot, you see a bar that represents 400 different verb types, and those occur virtually exclusively in the perfective. The remainder in the middle, in the valley nearly, so to speak, occurs to varying degrees in either aspect, and only the little bit in the middle of the plot contains equiprobable verbs, so verbs that occur nearly equally often in either aspect. And out of the nearly 1,800 verbs we looked at, there were only 200 that displayed this behavior, but that's what most of the literature has focused on. So this already shows that instead of there being a choice between aspects that the theory seems to offer, in practice, in usage, there is a very, very strong bias. Only 16% of all of the verbs shows the even distribution that theory would lead you to expect. Now, we did the same for tense, and simply plotting our data revealed very interesting patterns. We noticed a huge discrepancy in tense use here too. You see in the left plot, you see the distribution of the tense and the tense tags in the full corpus. And then on the right-hand side, you see the distribution of the tense tags after filtering in our 10 million sentence corpus. And you can see that the proportions are virtually identical. So our results should apply to the larger corpus as well. But as you can see here, there is a huge discrepancy with nearly 60% of all instances for present tense. And as you may remember, there is no spectral choice in the present, it's always imperfective. Then we have the 30% of cases that are past tense, that is the purple and the orange. And you can see that the purple is twice as large as the orange. And in the 10% of cases, that is future, which is the red. And then there's a sliver of blue. It's virtually exclusively perfective. So 9% of the cases is perfective future, and then 1% is imperfective future. So we can map these bias plots onto the spectral bias plots onto the tense plot. And then we see the following. So in the future on the left, you have more types that prefer imperfective, but overall there are more tokens of the types that prefer perfective, as shown by the red versus the thin blue sliver in the pie chart. And in the past, on the right-hand side, you have more types that prefer perfective, and overall, you also have more tokens of those types that prefer perfective, as you can see in the blue versus the orange slices in the pie chart. And what those plots taken together show is that aspect seems to be lexical. And there, grammatically different things are possible. In theory, different things are possible. But in practice, in usage, those possibilities are not necessarily exploited to the same extent for all verbs. And that gave us a very strong impression that aspect might indeed be lexical, and that, as our psychologist told us, these are all different words. Which led us to the computational modeling study. So if the hypothesis holds that aspect is lexical, then it should be possible to learn aspect from lexical information alone. And we tested this hypothesis by letting our learning algorithm learn from contextual data. So first I'll tell you a little bit more about our algorithm. The algorithm that we're using is based on the Skorla and Wagner's model of classical conditioning. That's why you have the dog, the food, and the bell here on the slide. Haralbainen and Peter-Millen implemented this rule computationally, and it's known as the naive discriminative learner. So it's a model of associative learning. Associative learning means that it's a learning process in which a new response becomes associated with a particular stimulus. Naive in this case means that it assumes that all of the outcomes are independent, and discriminative points to the fact that it involves discriminating between classes. And these cues and these outcomes that are linked to each other or are not linked to each other, they occur in learning events. And we'll say a little bit more about that later. So this is the formula behind the algorithm. As the mathematicians will tell you, it's very simple. The model indeed stands out because it is very simple when you think of the deep learning models that are currently available, and it is very simple. It's also very attractive because of its simplicity, because it remains possible to understand what is going on. We don't need to come up with a whole new science of understanding what the different birds are doing, for example. At the same time, that as it is simple, it's also very powerful. It has been used to explain a range of empirical learning phenomena. And it's also biologically plausible. It's rooted, it's based on research with animals and humans. Very simply put, this algorithm learns from exposure to data. It doesn't only learn from positive evidence, it also learns from negative evidence, and it learns from the mistakes that it makes. It's an error correction learning mechanism. I particularly like this slide, this slide design, which was proposed by Ksenia Misic from a friendly lab in Belgrade. So she really nicely summarized the rule. Basically, if there is no cue and there is no outcome, nothing will happen. But if there is a cue and there is an outcome, and these two occur reliably together, then an association will be formed. But if sometimes the cue occurs and you don't find a particular outcome, then after a little bit of initial enthusiasm, these relationships will fade away. Now, of course, the criticism can be raised and will be raised that, are we implying that detecting associations between formal cues and outcomes is all there is to human learning? Well, obviously that is not what we are implying, but what we're trying to do is fully understand how much of a user's knowledge can be attributed to this very simple cue outcome association mechanism. So associations between information that is available in the input. Of course, language learners have access to other information than the formal information available in the speech signal. They also have access to information from the wider experiential context. And of course, this rich conceptual structure is unlikely to be reducible to learning associations between formal cues and outcomes in textual input alone, but those associations may make a bigger contribution than is currently acknowledged, and we'd like to learn more about that. So now, what goes into a model like this? So as I said, those cues and outcomes that we're interested in occur in learning events, and for language, a natural learning event would be a sentence. So we take any sentences that occur in the corpus, and then we translate those into cues. Since we wanted to see whether an aspect was learnable from context, we fed our model context as cues, and we called these anagrams. So we had word chunks that varied in length from 1 to 4 words that were fed into the model. What we also gave the model was what we call the superlemma. This is the aspectual pair of the imperfective and the perfective infinitive, and those we used as concept placeholders, because of course, once we remove the verb from the context, because we want to see which aspect is going to be used, it would be really unfair on the model not to only ask it which aspect would be used, but also ask it what actually the speaker is going to say. So this superlemma is a placeholder for our concept, so to speak. And because tense was so important in our data, we also gave it tense information. Now, Slavic languages aren't known for very complex tense systems. They basically have a past, a present, and a future, which came in very handy here. because it's as naive as things can get. So it's basically knowledge of whether something has already happened, is happening, or will happen. And this is something that children develop really early on. So it's not very sophisticated conceptual knowledge or linguistic knowledge that we are relying on here. And then the outcomes was in this case imperfective or perfective. Of course, our model doesn't know what imperfective and perfective means to a linguist. It's basically, is the form that would be used here classified as belonging to something we label imperfective or perfective. So to give you a bit of a visual representation, the algorithm tries to work out which contextual elements, maybe 2 grams, bigrams, or 4 grams, or cues such as present tense or future tense, are associated with which outcome label imperfective or perfective. And then gradually, as it works through the corpus data, it builds up associations. And we see cool blue relations here, for example, between the present and the perfective, because these don't go together. But we also see hot red relations between the future and the perfective, because these do co-occur. And as the model works its way through the sentences that the learning, through the sentences from which it learns, it adjusts its predictions based on the input it receives, and then also on the errors that it makes. And here are the results. So we ran a number of models. They're all listed on the slide. A number of different models, and they differed in the sense that they all included different cues. So we ran models that only used n-grams, we ran models that only used superlemmas, and then we use all kinds of combinations of these cues. And I've ranked the performance of the models according to the F1 score. So from bad to good. And we have run separate models for all of the verbs together versus for those verbs, only those 200 that were virtually equiprobable and occurred equally often in the imperfective as in the perfective. So when you look at the results for all 1,765 verb pairs, our algorithm achieves a score of 95 for predicting the imperfective and 90 for predicting the perfective, with a combination of conceptual information, so superlemmas, and tense information only. If we would rely on lexical information, so contextual information alone, we would get results that are a lot worse, with 81 for imperfective and 41 only for perfective. And if we'd rely on the conceptual information only, so what's contained in the verb, we would end up somewhere in between, with 86 for imperfective and 65 for perfective. And now, as you can see at the bottom, for the 282 equiprobable pairs, so pairs of which both the imperfective and the perfective were used roughly equally often, the tense model is the simplest and the best performing model, with scores of 93 and 94 for imperfective and for perfective. And these results were really good. Irina checked her code several times, because at some point we thought it was too good to be true. But of course, when you then compare to models that contain only n-grams or only superlemmas, you see that the results become quickly a lot worse. So in a sense, we could say that yes, the psychologists who were native speakers of a Slavic language were right when they followed their gut feeling and said, like, well, you know, these things really are different words. But what we hadn't expected is that tense would be so helpful in selecting which word to use, because this is because there's such a strong bias in usage. And that usage, of course, reflects not only how the world is, but also how the world is described, or rather when events in the world are described. And that appears to be very important. Just by way of joke, on this slide here, some things such as going extinct cannot be said to be happening in the present by one exemplar of the species. And that's why this cartoon is funny, at least to a linguist. Now, back to the model. So I also mentioned that contextual elements are important, and that linguists often point out that contextual elements can help you make a choice if the rules aren't sufficiently clear. And for this reason, contextual elements play a role in accounts of aspect and especially in explanation for foreign learners. But Laura Janda and her team established that these contextual elements are quite rare, which made them wonder how they could be useful for learning. When they are there, they're very helpful, but they're very rarely present. And I think that our model offers an interesting perspective on that question. So when we enriched our model with n-grams, the performance didn't improve, but it did allow us to compare the types of contextual elements that are important for the two types of verbs, so biased versus equiprobable. And when we compare to the corresponding model for all verbs, we see that more n-grams that express temporal information, especially repetition, and those are coded in yellow here on the slide, occur within the top cues for the use of imperfective aspect. And contextual elements expressing specific time points, I marked in green on the slide there, these appear to be very strongly related to the perfective. So, and this was only the case for the equiprobable verbs. So in other words, these markers may not occur very often when you look at all the verbs together, but they do occur basically where they are needed. And that is in cases where the lexeme itself isn't already strongly biased towards one aspect or the other. So when you're dealing with a concept that can occur in imperfective and perfective, you suddenly find these contextual cues that help you decide much more often. So if we go back to what we linguists used to offer, respectual pairs, rules, and contextual chunks, we see that that's actually what we offer is actually not what a model needs to learn to use aspect from the data. What it needs is individual forms, it needs information about tense, and it needs contextual chunks. Now, of course, as an angry reviewer told us a while ago when we presented a different language model based on this learning algorithm, this is inadequate as a model of human language learning, as human beings are not machines that merely associate cues and outcomes, but intelligent beings who understand what words and grammatical forms mean and use them because of what they mean. So just to be on the safe side, we ran another study, and this time it was it's a behavioral study. Because what linguistic approaches focus on, or what linguistic approaches to aspect have in common generally, is that they focus on the language system and how it encodes the temporal dimensions of experience. But they too leave the cognitive system of the language user out of the equation. So we wanted to see, you know, in addition to using computational methods, whether we could be heretic in a different way and see whether insights from cognition could shed light on linguistic debates. So this case study explicitly relies on memory research to find out how first language users process aspect, to see whether that insight can help us shape or create cognitively realistic accounts of a spectral knowledge. And this work is further along, and it's about to be published in the Journal of Cognitive Science. It was work done jointly with, again, with Peter Milin, but also with former postdocs, Rajan Medimorets, and one of our PhD students, Maciej Borowski. So to go into this study, I need to give you a little bit of background from 3 different angles. So first is a very short overview of theories of language cognition. And when you look at different theories, you will see that many subscribe to the distinction between grammar and lexicon, which was, of course, inherited from Chomskyan approaches. So cognitive scientists, often when they look at language, see the difference between the grammar and the lexicon, where grammar refers to, or where they use grammar to refer to rule-based procedures for which sequence and hierarchy detection is really important. So this would cover syntax and morphology, among other things. And then on the other side, there is something like the lexicon, which is used as a cover term for anything that relies on arbitrary associations or on idiosyncratic knowledge. So these could be simple words, but also morphological irregularities or chunks. And as I already said, this stems from different theories of linguistics. In generative frameworks, generally the lexicon-grammar split is maintained, although lexicon and grammar aren't necessarily interpreted in the everyday sense of the word. Whereas in usage-based approaches, you would think, or you would assume that grammar and lexicon are not opposed, but they are different on different places on a line, from more to less abstract form meaning mappings. And then there's a third set of theories, in this case, theories of memory, that also consist of two opposing poles, and that is, here in this case, is the difference between procedural memory and declarative memory. So in procedural memory, learning would be slow and very gradual, and it focuses, or it acquires knowledge of inflexible, consistent relationships. Whereas in a declarative mode, learning would be fast, and it focuses on flexible and relational information. Now, while learning in the procedural system may be slow, access is very fast, and it doesn't require conscious or intentional retrieval. On the other hand, learning in the declarative mode is fast, but access is very slow, and it requires conscious and intentional retrieval. And these two memories are also known as implicit versus explicit memory. And you can see that these things really nicely map on to each other. So to answer the question whether it makes sense to treat aspect, or whether it makes more sense to treat aspect as a grammatical phenomenon or as a lexical phenomenon, we based us precisely on this research on memory. And as I just said, there is a difference between declarative memory and procedural memory systems, and declarative memory systems are assumed to be needed to deal with the lexicon, whereas procedural systems would handle grammatical knowledge. And there's a nifty little but rarely used experimental paradigm that should show which memory system is most active, and it's called the dual task paradigm. I will tell you more about the dual task paradigm in a second, but as the name would make you suspect, you're asked to do two things at the same time. And if those two tasks compete for the same memory resources, processing is slowed down significantly and becomes more variable. So in this case, the split would be as follows. So this declarative memory or explicit memory is conscious, and it should be affected by a secondary task, whereas procedural memory is automatic, and it should not be, or should be less affected by a secondary task. And of course, then by seeing which linguistic phenomena are affected by the secondary task, we can see under which memory they resort, and then whether it would be more grammatical or more lexical in nature. So here's a brief overview of the dual task paradigm. So we used audio stimuli, which we generated using Google's cloud text-to-speech services. This is because some of the stimuli had to contain errors, and native speakers found it really hard to read sentences with errors as if nothing was going on. And we didn't want those small hesitations to give anything away to our experimental participants. So first, in what we call the single task condition, or the baseline condition, which is in red here, we ask participants to listen to sentences that contained a range of grammatical and lexical phenomena, and I will show you a few examples on the next slides. So they were given a stimulus to listen to, and then they had 5 seconds to judge the accuracy of the sentence, so to tell us whether the sentence they heard was correct or not, and we recorded how long it took to take a decision. Then next, in the concurrent task condition, we asked participants to do the same, while keeping in mind a sequence of 3 digits. So first we showed them 3 digits, like 3, 7, and 6, for example, and they had to keep this sequence in mind while listening to the stimulus sentence and assessing it for accuracy. And after they had rated the sentence as correct or incorrect, they were asked to type in the number sequence. And because keeping in mind the number sequence would impede access to declarative memory, which harbors the lexicon, but not so much procedural memory, which harbors grammar, we hope to see from how aspect would be affected, where it belongs, with grammar or with the lexicon. Now you can set this number of digits to anything really. We set it to 3, which is relatively low, but we had a good reason for doing so, and that is mainly because our earlier studies with a group of L1 Russian speakers who were very similar in terms of background and education, that showed that 20% of our participants could only hold 5 digits in memory if that was the only thing they were doing. So if we increase the number of digits, we would also increase the risk that no useful data would be returned. So we loaded their working memory, but not too much. So the crucial element, of course, here is that this experimental design would give you a different prediction. When you look at it from a generative perspective, then because they have this clear distinction between lexicon and grammar, there is also a clear prediction. Lexicon would be declarative, and that would be affected. Syntax is considered procedural, and that would not be affected. Now, in the from the usage-based point of view, things are slightly more complicated because we would assume there's a continuum between the lexicon and grammar, and the predictions are therefore less clear. So I'm not sure whether I should say the lexicon is more directly meaningful than morphology, and morphology is more directly meaningful than syntax, or whether I can swap places between syntax and morphology. So in this way, the flexibility of the usage-based approach made it quite hard to really verbalize a specific hypothesis. And our question was, of course, where will aspect fall? So here's a summary of the design of the grammaticality judgment task. All participants heard 192 Polish sentences in total across the study. The stimuli were divided into 2 sets of 96 sentences each, and 1 set was used per condition, so the single task condition or a dual task condition, and this was counterbalanced so that there was no link between condition and set. Within each set, half of the items were experimental and half were fillers, and within each of these subsets, half of the items were correct and half were incorrect. And this was so that participants couldn't develop a response strategy based on whether something was correct or incorrect, couldn't figure out which ones were the experimental and were the filler items. Now, let's have a look here at the stimuli. We used data from Polish, but I'm first going to give you some examples in English. So the first example is lexical in nature. We're having fast food, we're having quick food, where fast food is correct, but quick food would be incorrect. And then the third example is grammatical in nature. It's about the correct form of the pronoun given its function in context. So she said the police saved the dog is correct, but her said the police saved the dog is incorrect. And then the question is for us about the example here in the middle, which has to do with aspect. Hopefully we will meet him next season. Hopefully we are meeting him next season. Which one's correct, which one's incorrect, and how does the way in which you respond to this item compare to how you respond to clearly lexical versus clearly grammatical items. So here are a few examples of the error types in Polish. So we had one type of errors, obviously, that was related to aspect. Different from the computational study, here we did include other forms alongside the indicative. So we have some infinitives as well. We also included some errors against case, like, for example, usually after work, I lack the motivation to go to the gym, where motivation was given in the instrumental, but it should have been a genitive. We also had errors against subordination, for which Polish has quite a complex system. So here, instead of a that clause, so we needed a that clause with a past tense, but we used an infinitive. And then for the lexical items, we had collocation. So here, for example, we were looking at the collocation traffic regulations, which you can say in Polish, it should be przepis, but not zapis drogowy. So these were the types of errors that we hid in the sentences. And we ran the experiment on 48 native Polish speakers. They were all very talented linguists. And so it's important to note that they spoke between 1 and 6 foreign languages, most often German or French. And in addition to the grammaticality judgment task, we also asked them to carry out 2 other tasks that measured their ability to process things explicitly and implicitly. So for the explicit processing task, we used something that's called the Llama F task, and where a participant is shown a series of pictures that depict shapes and objects and a short description of those shapes and objects in an artificial language. And then the task is to figure out how the descriptions relate to the pictures, but in essence, of course, they're figuring out the grammar of that language. And then for the test of implicit processing or implicit learning, we used a serial reaction time task, which measures memory for statistically consistent structure sequences. So for example, a dot will appear on the screen in one of 4 positions, up, down, left, and right. For part of the experiment, the dot appears in a random pattern, but for another part of the experiment, the dot appears in a patterned fashion. And then we can see by how quickly the respondents click the button as soon as they see the dot, whether they have predicted it. And of course, you can only make predictions if there's a pattern. You cannot predict anything that's random. So to test our hypothesis, we constructed a linguistic model in which type interacts with condition. So the type of error, aspect, case, subordination, and collocation. We wanted to see whether responses are different depending on the condition, which is a single task versus the concurrent task condition. And we also constructed a learning model where we tested whether the implicit versus implicit learning abilities were affected by condition. Interestingly is that those 2 tests on implicit versus explicit learning abilities were not at all related. So we then analyzed the data from this experiment, from this study in 3 different ways. So recall that respondents were asked to judge whether a sentence was correct or incorrect by pressing a button. So we have the speed of their judgment. We also have the accuracy of their judgment. And then finally, the consistency of the time they took to make a judgment. So when we looked at interaction between condition and type, we found that all type-wise comparisons were significant, with lexicon most affected by the dual task demands, followed by syntax, followed by case, and aspect being least affected. So on this task, aspect would clearly fall under procedural memory, whereas the lexicon would clearly fall under declarative memory. When we look at the at how the relationship was between the condition and both learning measures, we also saw that there was a significant interaction. Generally, all learners, all types of learners were affected by concurrent task demands, but they were affected differently. So strong implicit learners were less affected by the concurrent task and significantly less than the other 3 levels of implicit learners. And this makes sense because procedural or implicit learning would be the ability that's not affected by this manipulation. Whereas poor explicit learners we found that they were no longer different from strong explicit learners in the concurrent condition. And this also makes sense because explicit learning skills, declarative skills, are exactly those that you cannot rely on in the concurrent condition. It's exactly those that the digit span task would knock out. We also looked at the accuracy of the judgment, and overall the sentences were judged very accurately. That is, the judgment of the participants matched the judgment that we as experimenters had made, and only 7% of the data was judged differently. We found a direct main effect of type, but not of condition on accuracy. So generally, there was a higher match between the participant and the experimenter judgment for subordination and case, and there was a lower match for aspect and collocation. And this didn't change between the single and the concurrent task conditions. And then finally, we looked at the consistency of judgment. For this, we used something that's called the rolling standard deviation. And that's a measure that is identical to something that's called the coefficient of variation, which has been used extensively in second language acquisition research to measure automaticity. And here too, we have a main effect of type and condition, but we see the same two groups recur. So you have again syntax and case that showed fewer errors, also showed less variability in time to decision, whereas collocation and aspect that showed slightly more errors also show more variability in time to decision. So to wrap up these studies, we can say that when you look across conditions, it's clear from the response to the experimental manipulation that lexical collocations belong to declarative memory and aspect would fall under procedural memory, with syntax and morphology somewhere in between. But when you look at the behavior within conditions, you see that lexical collocations and aspect are very often appear in the same way, in that it takes more time to judgment, you make more errors, and you are more variable in your judgment. So lexical aspect and collocations go together there, with morphology and syntax going towards the procedural side of the decline. So what does that tell us about aspect? As I said, within conditions, it seems that aspect is slower to judge, more prone to error, more variable, just like lexical items. But across conditions, it was clearly the one that was least affected, which is, would put it in the procedural domain. And we think that this coincides with what we found in the computational modeling study. So there is a lexical component. There's no need for context, really. There's no real choice, as we saw in the plots earlier on. But somehow when you're put under pressure, you can make this decision really quickly. There is some kind of shortcut available to aspect that's not available to lexical elements. And this shortcut may well be tense, because there is this inflexible and consistent relationship between aspect and tense that we saw in the data. Now, this is a bit of an uncertain conclusion to an extent. The categories, the nice, neat categories that we started with, don't exist anymore. And I'd like to wrap up on this uncertain note, because the case studies present a case against too rigid an interpretation of categories or structures of any kind. The patterns that language users detect in the data may not be what we as linguists expect, and they may not look as neat as we expect, but that's what emerges when we let learning play a role, and learning certainly plays a role in building a system from usage. And so this is something that I think we as usage-based linguists might want to consider doing a bit more of, because it helps us commit to the usage-based stance that abstractions would emerge from exposure to usage. Usage is messy, so how could our abstractions be neat and tidy? And we think that the approach that we are trying to develop provides valuable insights into the kinds of generalizations or abstractions that can lay claim to cognitive plausibility. And it also sheds light on what kind of information these categories might contain. And this may ultimately change the way in which we think and write about language. Thank you.
Yes, thank you very much for this very insightful and very clear talk. We have time for questions now. I don't see any questions in the chat, or not yet, but I have one.
Okay.
If I may start, one, it's a very general question, which probably relates more to the first study that you showed rather than to the second one. And it has something to do with the fact that you're basically looking at two dimensions that are variable. On the one hand, you have a learning algorithm, and on the other hand, you have an input parameters, and both are variable. And you can, if you believe in one learning algorithm, then you can say, okay, this seems to show that users use this information to arrive at a certain effect. But on the other hand, if you're pretty certain about what the input would be, then that would teach you something about what the best or the probable algorithms would be. So how would you deal with that methodological duality, let's say?
Yeah, that's a great question. I think maybe Peter will want to unmute here. It's a discussion that we very often have, because when you deal with the computational algorithm, as you said, you need to give it something. But in giving it something, or in deciding what to give it, you have already made very important decisions. And we don't have a very good answer to that, other than it's important to state what you feed in and why you do that. Because it's exactly as you say, that bit is variable, and now the algorithm is variable, and there are so many combinations that you could make. So one of the ways in which we approach this, but I'm not saying it's a solution, is that we try to give it as little as possible, and whatever we give it, we try to keep as what we call naive as possible. So we try to limit ourselves to giving it information that we think untrained speakers of a language would have access to. Of course, you know, that's a very difficult discussion because we give it words, right?
Yes.
Do untrained speakers of a language really have words? We know that people who can read have words, but you already speak the language before you learn to read. So I think this is really an epistemological, a very fundamental problem of this type of any type of research. That is, what do you feed it, and what kind of decisions have you already made at that point? Yes. And then, yeah, as you said, the algorithm also differs. So very often we try several algorithms. And again, our preference is for those that are simple, because those are the only ones we can really understand. And then once we have a handle on the very simple thing, we can start adding some bells and whistles. Yeah, as you saw, Irene will remember how many different combinations she ran of just input cues. But because
one of the difficulties confronting us these days is precisely that the algorithms that perform best are very often the least transparent ones, the ones that are most difficult to understand. So,
if I can jump in, I don't know whether you hear me or not.
We cannot see you,
yes.
Peter.
Yes, but we do hear you.
I can turn on the camera as well. It's fine. You told me to unmute. I'm very, I'm compliant. You said just to unmute. Now I can. Okay. Hi everybody. Just to kind of reiterate what Dagmar said, is basically we are literally using the simplest learning algorithm of them all. So basically it has only one free parameter, which we very, very rarely tune. And for particular purposes, it's always set to the same standardly used value, which is a very small change in an update, so to say. So there is this, we are compliant also with this principle of minimal disturbance, as it's called in machine learning. And then those other algorithms are all close relatives to this Widorf-Hoff or Escola-Wagner, which is effectively the same algorithm coming from different disciplines. So those relatives are in a specific way generalizations of that simplest algorithm, and then you know what they add, what flexibility they add. It's also very interesting. We run some other studies in parallel which uses this state-of-the-art, most complex systems such as BERT, and then we get surprising results that BERT does better than humans. But we don't know exactly why. And then the simple algorithm, which is Widrov-Hoff or NDL, it does, or it approximately is as good as humans if fed with the right type of data. And you're right, there are two problems. One is the data, which we want never to give for free sophisticated linguistic information. I don't know, syllable structure, or, you know, all kinds of for free, which many of those algorithms are getting for free, and then they achieve quite good performance. So that's why we like to stay naive on both sides, in the sense of the data and in the sense of the algorithm. Of the
it is an issue in talking to computational scientists, because they would stuck to their BERT-based deep learning approaches, right? It's something you mentioned in the introduction.
But their goal is different. I mean, it's not my role to defend them, but they want to achieve performance. They have applied goals, so to say. They are not necessarily helpful to understand. This is an old stuff. In philosophy of science, when they say, you know, we will not learn much about birds, how birds are flying, if we look at airplanes, because, you know, this is exactly what so airplanes are flying, but not really like birds. So I think that we in our team also want to understand how humans are doing this job.
How humans are flying.
The best bit is when the system makes errors, and those errors are the same as the errors that we see in humans.
Now I have another question in relation to that, which is, would you envisage possible individual differences in the learning algorithms, in the learning strategies that people have? Obviously, they would have differences in the input parameters that they use. But would there also be variation on the, let's say, on the algorithmic side, on the learning side?
Yeah, I think we think that's very well possible, and we've been discussing ways in which we could investigate this. So we've done a study in which we tuned the algorithm, or the settings of the algorithm, backwards towards the individual learners to see what settings would fit an individual learner best. And there were indeed some difference related to working memory and things like that. But that's kind of that's done in a backward fashion. So that's a very simple approach. But yeah, it's perfectly well possible that not everybody learns in an error-driven fashion, or that some people, as Peter says, there are a few parameters we could tweak, that some people are more susceptible to correction from error, or that other people just learn much faster. And these are all things, this is just the beginning of, I think, a very exciting journey. But sometimes it seems there are more questions to ask than we've done so far.
Yes, that's the characteristic of a good research paradigm. So that's no problem. Actually, since I don't see any questions in the chat, perhaps this is a nice optimistic perspective to end with.
Okay.
If that's okay. Yes.
Good.
Well,
thank you so
then
much,
I want to thank you once again, and see you soon in another context, hopefully.